Combinatorics can be a challenging field because sometimes it's hard to conceptualize how to arrange things to count them properly. And so combinations is no exception to this. So the idea is fairly straightforward at first, right? It says that we have this pool, if you will, of n objects. We have a total of n objects in here. And what we want to do is we want to figure out and count the number of ways of selecting r of them where r is less than or equal to n. So you can't draw more objects than you have. And so the question is, how many, right? How many of these types of sets of r can you collect? And in particular, the way in which we're counting these groups is you can't draw the same element twice. So these have to be distinct elements within that population set. And also, we don't want to count all the rearrangements of each of those r things. So if the number was, if we were drawing digits and you drew 1, 2, 3, you would not want to count that different as 1, 3, 2, or for that matter, 2, 1, 3, 2, 3, 1, 3, 1, 2, or 3, 2, 1. You would want to count all these as the same. At least that's the context here. It's not always true, right? Maybe the sequences do indicate different things, but if these are 3 people being selected to, let's say, hand out papers in a classroom, well, then it doesn't matter what order you draw those same 3 people in. That counts as one group. So the first kind of more obvious application of combinations is when we're sort of physically drawing objects. So let's imagine that there are 8 wires. So we have these. Let's pretend these are the ends of those 8 wires: 4, 5, 6, 7, 8. And what we want to do is we need to connect 2 of them in order for the circuit to turn on. And we don't really know which 2 wires those are, so we start testing pairs of wires. So maybe we draw those 2 and we connect them, and then we draw those 2 and those 2, and we kind of keep on going until we found a pair, and then we test these 2 and these 2 and so on. Now we have to ask ourselves, okay, is the count, all right, so the question is how many pairs of wires must be tested at most? We say at most because, of course you may pick the 2 right wires on the first try, but possibly, it could be the last 2 in the entire sequence that you could finally connect the last 2, and those cause the circuit to turn on. So the way we want to approach this is we want to say, all right, well, we have 8 things. We have n equals 8 things, and we're going to draw r of them. And we're, of course, not going to draw the same wire twice. When we select 2, I want to select 2 different ones because, of course, you're not going to connect a wire to itself. And the order in which you draw them doesn't matter. In other words, drawing wire 1 and wire 2 is the same thing as drawing wire 2 and wire 1 because you're connecting them, and they're both going to touch, right? So the idea here is that if I'm going to draw 2 of them, well, if I started off with just this idea of there are 8 wires for the first choice and then 7 wires for the second choice, that's 56 wires. But remember, when we do this and we select wire 1, we may select wire 2 next, right? It could be any wire from wire 2 down to wire 8. But let's suppose that you draw wire 2 first. Well, now you can draw wire 1, wire 3, all the way down to wire 8. And you see, of course, that wire 2, wire 1 is being counted twice, just in different rearrangements. So we learned that we need to divide this by r factorial, which is the number of ways of rearranging those r items. And, well, there's 2 choices for the first, and then 1 choice for the second. So that gives us our 2 instances of the same 2 wires. So we would just divide that by 2, and that gives us 28. Now you get the same answer if you used a calculator to compute the number of combinations. 8 things in total, draw 2 of them, you would get this answer of 28. So this is the mathematical way of calculating, and notice that you can multiply and divide, but you have to divide by the number of rearrangements. If the order in which you connected the wires for some reason made a difference, which doesn't make sense here, then you would leave it as 56. Here's one more example. A company manufactures 10 routers to check for quality control Maybe they can't select all of them for quality control, so they pick 3 of them at random and they test those 3 and use that as an assessment. How many ways are there to select 3 for testing? Well, once again, you can think about this as, you can select router 1 all the way down to router 10, and then, this could be router 2 all the way down to router 10, and then if router 1, router 2, then it could be router 3 all the way down to router 10. So we're just eliminating that possibility. So of course, you can't select the same router 3 times because you want to select 3 different routers. And keep in mind that this appearance, this R1, R2, R3, could also show up as, so it could be R1, R2, R3, it could be R2, R1, R3, it could be R1, R3, R2, it could be R2, R3, R1. Hopefully you're getting the idea that there's going to be 6 of these, R3, R1, R2, R3, R2, R1. So there's 6 rearrangements of any 3 objects. So we could start this off again, and we could say, well, there are 10 routers that you can pick from, combined with 9 routers, combined with 8 routers. But then we have to divide by the number of ways that those same 3 could be rearranged. There are 6, right? That's 3 factorial ways to rearrange the same 3 objects. There's 3 possibilities for the first one that you select, 2 possibilities for the second, 1 possibility for the third. There's your 6. 10 times 9 times 8. That's going to give us 720 divided by 6. And 720 divided by 6, I think, comes out to 120. Just double check my math here, because sometimes 720 divided by 6 is, 120. Okay, so there are 120 different pairs of wires that you might have to check. Or sorry, that's the previous example. 3, so 120 different ways in which you could draw 3 routers out of 10 routers. And once again, you could just say that's the number of combinations of 10 objects. Select 3 of them, will give you 120. Okay, so notice that we're sort of drawing physical items, but sometimes the combinations, this isn't an issue with permutations, because you'll see in a moment that combinations is used more commonly in a lot of applications, and you'll see that it's just sort of natural. So in some cases, rather than picking objects, we're going to think about it as picking slots. Okay, specifically, when items are repeated, we cannot just multiply in the same way. I'll say right here, in the same way. For example, consider the word moon. And suppose we want to rearrange the letters. How many ways are there to do this? Well, one of the common mistakes is, well, there's 4 possibilities for the first letter, 3 for the second, 2 for the third, and 1 for the fourth. And when you multiply these together, you get 24. But here's the thing. If I just swap these 2 letters, the 2 O's in the middle, I still get the same word. Right? These represent the same word, and that's being counted in this 24. So moon and moon are each being counted individually, because we're just counting the O's being switched. Similarly, if we did M-N-O-O, and then we switched those 2 O's, that would still be M-N-O-O, right? So counting that 24 is actually not totally valid. We could also have M-O-N-O, M-O-N-O. That'll get counted twice when you swap those. And then you can have, well, we already have moon. We could have O-M-N-O, O-M-N-O. Again, those will get counted twice. Then we could also have O-O-M-N, and then O-O-M-N. That's going to get counted again in there, right? So that's all of the situations where we might imagine. Okay, so we have M-N-O-O, M-O-N-O, and then, well, actually, before I count this one here, let me try to keep this in better order. Then we could have the M in the second position, and then the N in the fourth position, excuse me, like that. And now we could move the M to the third position, and there's only one way to place that N for it to be in the remainder. And now we can do the same thing with n as the first letter. M could be the second letter. Okay, again, you'll have two counts there because those two O's could be swapped, and technically that's going to produce another in this 24. So 2, 4, 6, 8, 10, 12, 14. Let's keep going. So here's going to give us 16, N-O-M-O, N-O-M-O. That's 16. And then we'll have N-O-O-M, N-O-O-M. That's 18, right? We're counting 18 so far. 2, 4, 6, 8, 10, 12, 14, 16, 18. And now we could do all the situations where we shift the N over. So O-N-M-O, O-N-M-O. And then we could have O-N-N-O-M, O-N-O-M. And then shift the N one more position, O-O-N-M, O-O-N-M. Okay, I'm listing these all out because I want you to see how we're double counting everything. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's our 24, but really, we only see 12 words, right? We only see 12 of these words. This is an exclamation mark, not a factorial notation. There's two of them for emphasis. Okay, so here's the way we approach this. Anytime you have repeated letters, don't think about selecting letters into slots. Think about selecting slots into which to put your letters. So let's imagine it this way. I have 4 slots, and I'm going to select the 4 slots. So I'm going to pick a letter first, and I'm going to say, let's say that we pick an O. So we're going to take an O, and we're going to choose 2 slots. So perhaps it ends up being this one and this one. So the first question is, how many ways are there to select slots for the O's? Well, you could say that from 4 slots, you want to select 2 of them. And this is why I mentioned that combinations are a little more useful than permutations in general, because the order in which you select the 2 slots doesn't make a difference because it's the same letter. If you do the math on this, 4 times 3 over 2 factorial will get you 6. So there's 6 ways in which you could fill the slots with O's. So imagine that the O goes here and the O goes here. So the next thing we need to do is we need to we have 2 letters left, and we need to pick a slot for each of those letters. So let's just go with the M and say, all right, well, how many ways could I pick a slot in order to put an M into it? Well, clearly the M could go here or it could go here. So from the remaining 2 slots, I have 2 slots left, 1, 2 slots. From them, pick one of them and place the M in there. So there's 2 ways to do that. So there's 6 ways that I could lay down my 2 O's. Then from what's left, there are 2 ways in which I could lay down my 1 M. Again, it could either be here or here. And let's just say my M goes there. The N is an obvious one because, well, once you've filled up 3 of those slots, there's only 1 left. So, it could only go here, but let's do the math on it. From 1 slot, pick 1 slot. There's 1 way to do that. Now we want to count all the different ways. So for each of these 6 ways, there are 2 ways to place your M's and 1 way to place your N. 6 times 2 times 1 is going to give us 12. Look at that. That matches up. And you might say, but you picked the O's first. What if you had picked the, say, the M first? You did the other letters first. Not to worry, my friends. It works exactly the same way. Let's say that we wanted to place our N first, okay? And so you would say, all right, well, the N could go in any one of these 4 slots. Perhaps it goes here. Well, how many ways are there for that to happen? From 4 slots, pick one of them. There's 4 ways. Now, by the way, these numbers are already different, and you're like, this can't be the same, Milos. Well, let's keep going. Now, let's say we want to place our O's, okay? Well, the O's would go in 2 slots, maybe here and here. How many ways are there to do that? Well, from 3 slots, pick 2 of them. That'll be 3, let's see, 3 times 2 over 2, which 2 factorial, which will give us 3. So there are 3 ways to do that. And already look at that. 4 times 3 is 12. Now, how many ways are there to place that last letter? Well, that last letter in this case is going to be the M. And, well, there's only one place you can place that M. This is just one example. I'm just setting it up kind of visually so you can see what we're physically doing. And so from one slot, that last letter will always just have one way to be placed. And notice that you still get 12 when you multiply these together. So it doesn't matter how you do it. But notice that whenever you have repetitions, when items are repeated, you have a certain letter or character or whatever that has more than one instance of it, you got to be careful with the multiplication. Now, this problem wouldn't exist if the letters were all distinct. So like look at the word cars. Each letter appears exactly once. And so in this case, you could approach it the same way as above. You would say, I have 4 slots. There's 1 C. So how many ways are there to put that 1 C? Well, there's 4 ways. And then there's 3 places in which you could place an A and 2 places in which you could place an R and only 1 place in which you could place an S. So in this case, because none of them are repeated, the 4 choices here are distinct. The 3 choices here are all distinct. The 2 choices are distinct. The 1 choice here is distinct, and this is 4 factorial, which would be 24. Okay, so because a letter is repeated, you can see that we don't actually end up with 24. We end up with fewer because swapping the same letter doesn't produce a new word. Here's another example of where you see this commonly in bit strings, where you're dealing with 1s and 0s. You're dealing with binary. And let's just say that we have a bit string that has 3 1s and 4 0s. How many unique bit strings can be generated with these particular bits? Well, so I have 7 bits in total, right? And I could say that, this is a 1, 1, 0, and then my third one, and then the remaining ones are all zeros. Once again, I can't go 7 times 6 times 5 times 4 times 3 times 2 times 1 because of the fact that, well, I only have 2 distinct, think about it as letters if you want. I know they're numbers, but you have 2 distinct things and you're going to produce 7 instances of them in total. So once again, let's approach this through the avenue of picking slots. So my first step will be, and it doesn't matter whether you want to place your 1s or your 0s because, well, once you place your 1s, there's only one way to place the 0s. Or once you place your 0s, there's only one way to then place the 1s. You'll see what I mean. So let's say the 1s get placed. Okay, and so how many ways are there to do that? Well, I have 7 slots, and I'm going to pick 3 into which to place my 1. So perhaps it'll go here, here, and here. That'd be one way for that to happen. So if I do 7 combination 3, I get 35. So there are 35 ways to place down those 3 1s. They're all unique, believe it or not. You can try to count them all out if you want. But there are 35 ways. And no, we do not count the instance where we swap 1s because this is a combination in order. We don't want to count the rearrangements. So, okay, step 2. Now we would just need to say, well, now place your 0s. 0s get placed. Well, there's 4 0s and there's 4 slots, and the 4 0s are all the same, so there's only one way to do that. And the math will justify it. There are 4 slots. Pick 4 of those slots, and there is one way to do that. So when you multiply 35 by 1, you get 35 bit strings. If you did it the opposite way and you said, I'm going to place my 0s first, step 1, 0s get placed. Well, there would be 7 slots, select 4 of them, and guess what? This actually turns out to be 35. Again, shouldn't matter, right, whether you place your 1s first or your 0s first, because it's just, they're sort of complements of one another. And now the step 2 would be then to fill the remaining slots with 1. So imagine that these 4 orange slots were the ones filled with zeros. Well, now there's 3 ways to fill the 1s, and there's only one way you could do that. Oh, so 1s get placed, and again, 35 times 1 is 35 bit strings. So that means that there are 35 bit strings you could produce, not 7 factorial of them, which is actually a lot. All right, my friends, that's a way that we could work with combinations and applying them in sort of different ways to solve a diverse set of problems. So ask yourself, before you start multiplying, are there any elements that get repeated more than once?